Sorry, I was in the middle of that problem when the video cut me off. So if you've come here to see number 8 and following, you may want to watch the end of the first video because I got cut off in the middle of number 8 here. I just got to the point where I was saying, how did we get 9 from n minus 3 times n minus 4? Why does it have to be 9? Another way to do that, or once you get here, and I was saying just to be careful that you check that. Go back to the beginning here and go, okay, np5. If that's really supposed to be 9, let's look into that. 9p5, that would be 9 times 8 times 7 times 6 times 5. Does that really equal 30 times, and then it would be 9p3. 9 times 8 times 7. And just as before, just as the way we solve this, you can cancel all that stuff. You can cancel the 9, you can cancel the 8s, you can cancel the 7s, and yes, it does turn out that 6 times 5 equals 30. So yes, we should be starting with 9 in those cases. All right, 9 and 10 are about things like complementary, mutually exclusive, whoops, I didn't mean to cross that out, mutually exclusive, complementary, and the combination of those two things. So let's talk about what complementary means just for a second. Complementary would mean like two things that are together make up all the possibilities. So like the possibility that you would pass and the possibility that you would fail a test. Those two things are they don't overlap, and together they talk about everything that's actually possible. Like on the quiz, there was something like they described all the points in quadrants 1, 3, and 4, and then the complement of that would then be everything in quadrant 2. Mutually exclusive would be two things that can't both happen at the same time. And then, of course, you can have things that are any combination of those two things. All right, actually not any combination of that. We'll get into that. We're going to select two high school students randomly. Are these two events complementary, mutually exclusive, or what? The fact that the first student could be a male senior, and then that the first student selected is a female senior. Well, first of all, you can't have both those things happen at the same time. So we know that at least they're mutually exclusive. There's no way to have both these things happen together. Now, the other question is, do these two things, the possibility that could happen and the possibility that could happen, or say this event occurring and this event occurring, are those, thinking about complementary, this is a C, writing and talking at the same time, it's a C, exclusive. Could those two things happen and represent, if this doesn't happen, does this have to happen? In other words, do these things represent all the possibilities for being able to do this? Well, I don't think so, because it's talking about high school students being selected. It doesn't say that we're only talking about seniors here. In other words, you got the seniors, the juniors, the sophomores, and the freshmen. By selecting the first student, sure, if it was a senior, it would have to be male or female, but if it was not even a senior, there's other possibilities here. So, I mean, the first student could be a male junior, or it could be a female freshman or something like that. So together, this does not represent all the possibilities that are out there by A and B. A and B just doesn't cover everything. So together, these events are not complementary. If I leave the pen down, it's harder to read, but it's easier to write. Okay. Complementary, mutually exclusive, but not complementary. That's kind of what we're talking about. It's mutually exclusive, but not complementary. Okay, number 10, the first student selected is a male senior, and then combine that with the first student selected is a junior, sophomore, freshman, or female. Okay, that's a whole lot of stuff happening at once. First of all, are these even mutually exclusive? Male senior, and does this represent every other possibility? Junior, okay, if we think about the male seniors, who else is there other than male seniors? I mean, if it's male senior, does this include everybody that's not a male senior? Well, it includes all the junior, sophomore, and freshman. That's good, and it includes all the female seniors too. So, yes, these things are mutually exclusive, and I think they are also complementary. There's no way both can happen at the same time, and if you don't get one of these, you're going to have to get one of these. So, mutually exclusive takes forever for this pen to write correctly when I'm running out words. Exclusive and complementary. You know what I'm trying to write here, right? Okay, mutually exclusive and complementary. Notice they don't have, there's not even a choice here for complementary and not mutually exclusive. If you're complementary, you have to be mutually exclusive. Complementary means you're covering up everybody, but also at the same time it means, well, it's either this or it has to be that. There's no being this and that. There's no overlap. It's got to be, this male senior group or everybody else, and this is just a description of everybody else. So if it's complementary, it's got to be mutually exclusive. But if it's mutually exclusive, it could be complementary or not. Okay. All right. This one is actually kind of one of the most difficult ones I've seen in a while. 10% of the students in a military academy are female. If you select 3 students in a row, what's the probability that they're all of the same gender? Well, choosing 3 students in a row, how many possibilities are there? You could have that. You could have this. Of course, this is like without replacement, right? I could have this. I could have, it's like tossing a coin 3 times, right? That's all the ways you could start with male. Then there's all the ways to start with female. Now you don't have to do all this. You don't have to list all the possibilities. I'm trying to be systematic here, and I'm also trying to talk to you at the same time, which is kind of difficult to do. All right, I don't want to miss any, but as I'm doing this, we could talk about how many should there be. It's like tossing a coin 3 times. How many possibilities you have for the first coin? How many possibilities you have for the second coin? How many possibilities you have for the third coin? With replacement, or like one thing doesn't affect another, or the next, or after I do one, that possibility, whatever it is still available for the second one. So no matter what I do here, it's like without replacement. So it's like with replacement. If I pick female here, I put female back in for the second guess. It's like exponents. Okay, so there's the 8. This doesn't really look at there's 8 possibilities. Those are all different. Those are all equally likely. You have to get one of those 8. There's no overlap. But this is not flipping a coin. This is not equally likely that you pick a male or a female in the first place, because there's only 10% females. So we really just care about what's the probability that they are the same gender. Well, it could be that one or it could be that one. So let's find these 2 probabilities, and since they don't overlap and they're completely independent events, we can add them up. So the probability of male and male and male in this sort of conditional probability about the 10% business, probability the first person is male is 90%. Possibility that after that the second person is male, still 90%. Now you could argue, I think they take this out of the question, because this is sort of unknown. After you take one male out, the percentage of females left in the school are a little bit higher, because now there's one less male around, but or that could be chosen from. But we're going to assume that this place is so large that we're going to ignore that thing. In a deck of cards, that's not big enough to ignore. You have to consider, oh wait, we've taken one card out. There's only 51 left. There's one less of whatever I just picked. But here, we're going to assume that it's always going to be 10%, even if it's a little bit of a lie. But we just can't do anything about it right now because we don't know the size of the school. Okay, so 90 times 90 times 90% is like 90% cubed, which is, I believe, 72.9%, 0.729. Okay, and then female, same thing. It's just what's the probability the first one's female? Not very high, and second one is also not very high, and third one is also not very high. It's always 10% times 10% times 10%, which is really low. That would be, is that correct? Yeah, it's 1/1000th of a probability that that's going to happen. Now you might ask yourself, well, wait a minute, aren't these all supposed to be 1/8? Well, they were if they were coins and everything was fair, but I can't do that. Like, I don't even know the denominator here because the denominator is so bizarre because I've got this 10%, 90% thing going on. So I could find all these, and if I found all these with all my 10s and all my 90s, they should all add up to 1. But for this one, it's easy enough just to say, okay, what's this probability, what's this probability? I know they can be added because they don't overlap, and we can just go ahead and add that. So 729 plus, which is the vast majority of these probabilities, they're all going to be the same gender, they're all going to be boys, it's 0.73, or 73%. This is one of those problems that, yes, is as easy as it looks. They have to pick a restaurant, then they have to pick a movie theater, and then they have to find a gas station. This is kind of like, some people like to do this with the tree diagram. I have a choice of 12 restaurants, so you have the first place we start from, I have a choice of 12 restaurants, and this is going to take forever to draw, and I'm going to run out of room, but there's actually a choice of 12 branches on the restaurant decision. The next thing is for the movie theater. Each one of those would branch sort of twice for the movie theaters. I have 2 after that, and then on each, and I'd keep going, of course. Then on each one branch there, I have 3 gas stations I can choose from. So you can imagine all the little fingers of this tree here, all the way down. Really is just, well, there's gonna be 12 original branches. Each one of those branches twice, so that would be 24 branch tips at that point, and then each one of those 24 branches into 3 more. So that's why it's 12 times 2 times 3, which I don't care to do in my head. 12 times 2 times 3, which is, well, you know what? I could have done that in my head. Sorry about that. Is 72. This is the same kind of thing. How many ways are there to answer each question as you go through this? The first 10 are true, false. I'm not going to draw all those blanks. There's the true, false section. That's a T. And then after that, so and, I can multiply. I have the 5 multiple choice questions. And those each have 4 possibilities. Yeah, and then I have 4 multiple choice that have 5 choices. For the true false, it's going to be, well, there's 2 possibilities for each answer as I keep going through this. So this is going to be like 2 to the 10th power. I see a lot of people doing 10 to the 2nd power, which is not the way to do this, because if you think about it, I have 2 choices for the first one, 2 choices for the second one, 2 choices for the third one, and means multiply. I'm multiplying up a string of 2's, not a short string of 10's. This is the one where they all had 4 choices. How many of them have 4 choices? 5 questions, 4 choices. That's 4 times 4 times 4 times 4 times 4. And then 4 questions with 5 choices. That's not too long to write out. I'll just write that out. If you look at that carefully, that's 5 to the 4th power. Okay, now here's a great big multiplication problem I really don't care to do without the calculator. 2 to the 10th. 2 to the 10th times 4 to the 5th times 5 to the 4th. And that's a huge number, and it's, whoa, it's not even scientific notation. 655, 360, and 3 more zeros. So can I remember that? So it's, yeah, it's like over half of a billion there. This question is quite bizarre. It's about using, they just threw some random digits at you, and they're saying, let's just use this, because you could toss coins, you could roll dice to run any kind of simulation, or you could use a random number generator. And they're trying to make you use this random number generator to see what you get. And because there's more than 25 in this group, even different people are going to get different answers. So they want us to think about trying to see if 5 trains are going to arrive on time. The probability that it arrives on time is 70%. That's really low. It's way worse than the airlines. And notice how these are organized into little packets of 5. I think that's because they want you to take one of these and go, okay, let's let those 5 numbers represent 5 trains, and let's see which ones are going to happen, are going to show up on time. Let's do that. I don't know why they say circle the first digit and the last digit used in your simulation. I'm just going to pick a random sort of group of 25 of these little sets. It says conduct 25 trials to see if 5 trains run at a time. So I need 25 groups of 5 digits. These are all in groups of 5 digits. I just pick 25 of them. So I don't know. Let's do something sort of central here. These are in groups of 3. So if I pick 8 columns, let's do these 8 columns and then one more number. So there's 1, 2, 3, 4, 5, 6, 7, 8, and because I said it was central, let's pick that one. So here's 25 little sets of numbers. The other thing is, okay, how am I going to use these little 5 numbers to figure out if the train was on time or not? Well, there's 10 digits that are possible in any one of these things. Let's just say that a 0 through 7 implies that the thing was on time. It's like if I roll a 0 through 7 on my, oh wait, that's 8, isn't it? Let's say 6 then. That would be too much. This is 70% of the time. That means on time if it's 6 or below. And let's say if I get a 7, 8, or 9, that's the other 30%. Let's say that it's not. So these are complementary. And that'll represent the times when it's not on time. So 70% of the time, if you notice, if I do this right, 70% of the time it's going to be a number between 0 and 6 if this is truly random. And 30% of the time it's not going to be on time. So now I look through all these trials and I go, okay, which ones of these, the thing that's favorable here is that all 5 trains will be on time. Let me go to the highlighter here. Yeah, good. And let's say, looking at trial, this is the first trial here, is that were all the trains on time here?